I will give you some more information about the new version, ProTOp 5.0, and I set up an agenda. First, I'd like to introduce me and my sales guy, then a few words about the company I'm working for, GIA Informatik AG, and then we'll talk quite a lot about the news in ProTOp, the topology optimization solution from CAESS, and there are very exciting news about the new interface, the user interface, which is much easier to use. Then the topic will be about the new help documentation dialogues. I will talk a little bit about the new internal data structure, about new material laws, and about the new solution within ProTOp. We are now able to do mesh refinements within ProTOp, and quite exciting news is also the new combination capabilities from load and constraint sets. We can, let's say, analyze our design room, our components within maximum and minimum configuration, and we'll see that the solver is much quicker than before, so there is a huge speed up in solving process, and we'll also have new optimization options in ProTOp. And one of the most exciting things is that now we can easily export wavefront surfaces in order to reproduce the parts in our CAD system. And of course, the most of the things I will show you in live demos. I guess we'll do here a nice lattice shell component. And at the end of the day, we have a Q&A session. Please write down your questions in the chat panel or in the question folder of GoToWebinar panel. Let's start with the presenter for today. My name is Urs Simler. Simler means I'm the simulation expert in the CAD environment. I'm working for a company called GIA Informatik AG, and this is my colleague Daniel Losley. He's our sales guy. If you have any commercial questions about ProTOp, then you can contact him. Few words about GIA Informatik AG. We're located in the center of Switzerland. We have about 150 employees, and we belong to the Müller-Martini Group. Müller-Martini Group produces machines after, let's say, printing process, so cutting machines, machines for producing books and that kind of stuff. GIA Informatik AG is a SAP reseller. We are providing IT services and also services for the CAD and PLM environment, and we like to have a successful customers, and therefore we are helping our customer with the implementation. We are doing support, and we are also doing training and consulting in our in-house training center or at the customer. In the CAD PLM environment, working with partners. Here you can see some of our partners, of our software partners. So as I mentioned, we are doing sales training and consulting mainly with PTC products, PTC Creo Parametric, Creo Elements Direct, Windchill, MatCAD, ThingWorx, Gate. And beside that, one of our main partners is CAESS, and they have a very nice topology optimization software which connects with all the CAD systems like Creo Parametric, Creo Elements Direct, SolidWorks, Siemens NX, CATIA, and so on. And beside topology optimization, we're also doing CFD simulation with Flow EFD from Mentor Graphics, and we also sell solutions from the TechSoft company, an Austrian company, and the German company called Software Factory. By the way, we are monitoring some customer system, PDM system from customers. We have a PDM ERP interface, and as I mentioned before, we have an in-house training center in Oftringen. And our team is quite experienced. We have an experience of about 135 man-years. Let's have a look at the new version of ProTOp. ProTOp is released or was released at the beginning of March this year with all the functionalities, with all the stuff inside, and we have quite a lot of exciting news in ProTOp. The first thing is when we are looking at a new interface, we can see it's more intuitive. It's I would say it's much easier to learn than the old version 4.6, and it's flexible, the user interface, and so you can learn it in a very, very short time, because there's also a nice help documentation in ProTOp. And because, let's say, this software is designed by engineers for engineers, it has a very good help documentation. And the internal data structure of ProTOp was redesigned in order to have, let's say, better let's say, capabilities for the futures. And by the way, the new structure of ProTOp improves the efficiency of the software. And as a new material though, we now have a new capability inside called elastic orthotropic material. I mean, by the way, we can deal with elastic material, we can do with semi-plastic material or contact material. So we have now a new material type. One of the most exciting things is now the capability in ProTOp to do mesh refinement. So that means at the first step we are bringing in from our CAD system or from the FEM system of our CAD solution, we are bringing in a mesh. It can be quite coarse. Then we are doing some, let's say, optimizations. And in a certain state we need, let's say, a mesh which is more dense. And now we have capabilities inside ProTOp to do a mesh refinement, and there is also an estimation about how much RAM we need for solving, let's say, dense mesh. That means we do not have to go back for, let's say, our FEM system or CAD system to do there the mesh refinement and to switch backward and forward. So now we can do it directly, and that speeds up the process quite a lot, and it's, let's say, much easier for the user to do that. I will show that later on in the live presentation. New capabilities of combined load and constraint sets gives us a speed up of the solving process, and especially when it goes for contact or plasticity analysis, we can really speed up the solving process. A new capability is the design analysis. We are doing a configuration here on that wheel, let's say with lattice structure. Then we have an easy way to see, let's say, minimal, maximal configuration or actual configuration. We even can go in and change here the configuration to see our, let's say, design room limits on upper, lower, or configured configuration. And as I mentioned here in that area here, I can change my configuration, I can suppress, toggle some of my configuration features. As I mentioned before, the solving process was speeded up quite a lot, so we see, okay, the consumption of RAM went down and even the solving time is going down with the new version, and very nice, you get an information what is the performance of your machine, how many elements can you solve with the amount of RAM you have on your computer. And ProTOp now includes also some new boundary condition options when we are thinking about, let's say, the constraints here. Then here the displacement boundaries, and here on that side we have our, let's say, forces, and now we can set these options here in that area in order to get a specific behavior. So it means not allowed here with that options to take away the material of the constraint and load regions. Here it's only allowed to take away the constraint regions. Here it's only allowed to take away some forced regions, and here it's allowed to take away both. So this gives us more flexibility in the area of our loadings and of our constraints. And for me, new highlight when it comes to the end to our topology optimization, we are getting a new Bionic structure, and we have to let's smooth the surfaces. We have to remove peaks, to refine triangles, and for that reason we got a nice new tool, and in this nice new tool it's much easier to smooth and simplify those surfaces and this Bionic structure. So it's easier to smooth them, and it's easier to use them later on the CAD system, because we brought in a new algorithm for simplifying the model, and one new simplification can be used as a OBG export. OBG is the wavefront format, and the most of CAD system, they are supporting this OBG data form, and later on we can read in that OBG surfaces in order to do the redesign in our CAD system. I will show that later on in the live demonstration. So that's very important, and when you're thinking about cryoparametric, in cryoparametric 4.0, we have this free option to import this OBG data. Okay, and that gives me capability in cryoparametric to import this OBG data and to do some validation calculation with that capability. I'll show that also later on, or right now in the live demonstration. So now it's live demonstration. PowerPoint is finished, and I'd like to show here the process on a lattice shell component, and I will start in my CAD system, cryoparametric. I will do first here the model preparation. I will transfer, let's say, the FEM model to ProTOp, the new version 5.0. I will do some topology optimization, standard, doing some configurations with shells and lattices, and then at the end of the day I will export an OBG file, and this OBG file will be read into my CAD system in cryoparametric, and with, let's say, the new geometry I will do a validation analysis in my FEM system of my CAD system. This is called CryoSimulate. So let's start. With that one, we're going for Creo parametric. In Creo parametric, I'm going to open my component here. Component is loaded, and I will here reach Creo Simulate. In Creo Simulate, I will use here the FEM mode in order to get some edge meshes. And of course, here I set it up some volume regions. A volume region, let's say, in the back, a volume region in the front in order to get a symmetric model. And I assigned some material to the front region, to the back region, and to the rest of my component. And because the rest of my component gets the name underline fix, ProTOp will recognize this region, fixed region later on. Here I brought in a constraint set. I constrained the holes in all directions here, red highlighted, and on the top the hole is loaded in, let's say, 5 direction. Okay, so I created 5 load sets, and here the last load sets with all these little pressures, they are used for later shell configuration. And ProTOp will take them, and especially this load set will create some surface regions for later use. Here I can export, or I can connect my model with ProTOp. ProTOp should start, I guess, yes, on the right screen. Good luck for me. So I had some difficulties at the beginning to set up my screens. ProTOp is starting here, new version, and I can import my model. Of course, as I mentioned before, you can also connect ProTOp with other CAD system, with other simulation solution from SolidWorks, Siemens NX, CATIA, and so on. And here I have my new model, the new interface here. Let's take white background. Here we can show, scale, panel, all that kind of stuff. Here I have, let's say, our views from front, from right, and so on. Here we can set up some cross sections. Okay, and here we can take some screenshots. We can open a window, browse window of my area where I'm working. Here is a logger information, and here is my help information about dialogues and so on. Okay, and I can hide my project area, commands area, or graphics area. So at the beginning I'm just jumping into optimization, and I say, okay, I want to optimize my component. I'm just starting my session here. So by default, ProTOp is set it up to get, let's say, to reduce my blue volume to 50% without doing, let's say, some additional constraints. Here ProTOp is analyzing my part, and it's taking out the material in order to, let's say, to feed a 3D printer. So there are no restrictions on it, on how this component will be produced later on. So if I'm going for my cross-section, I can see this is a really a topology which can only be printed, can only be 3D printed. So I'm switching off here my cross-section again. Okay, and I'm, let's say, going to stop this process because I do not have a 3D printer here in my office. So I'm stopping here the cycles. Okay, and I want to bring in, let's say, some additional information how this component is produced. We call it here under the Opt Model tab, we call it here technological constraint. So if I'm going here for technological constraint here, I can ask my help documentation, what's that technological constraint? Here I'm getting all the information, what's mentioned with it, and I will, let's say, bring in some technological constraint where I'm going to say, okay, I want to have here a divider plane, and here I want to bring in some draft angles. So in order to, let's say, do a molded part or a casted part, that can be improved. That can be defined here with the technological constraints. So I'm setting up some technological constraints here. Okay, and now I will be asked to which volume will this be applied. So I'm setting up the constraint type. I want to have a plane symmetry, and this should act here on which volume. I can select here the volumes, or now I can go in and I can edit my volumes. I'm creating a new one, maybe called opt-all, and opt-all includes, let's say, the back volume or the back and the front volume here. Okay, so I created a new region here, and by typing on maybe the z-axis, you'll see, okay, now my component is getting symmetric, and here, of course, I have to select my newly created volume. Okay, that means now this is symmetric on that plane. I want to have an additional symmetry, so I'm copying that data here, and I'm just changing my axis of my coordinate system. In that case, it should be x-axis, and you see, okay, plane is changing, and now the component has to be symmetric to that plane here. And as a last thing, I'm adding a new copy, and in that case I want to define a B unidirectional open constraint, which goes to another plane here. That's the z-axis. That means now this is the divider plane, and by typing in a draft angle of 6 degrees, okay, the component or the volume I selected is forced to get here some, let's say, draft angles. Okay, it's done right now, and you see here all the constraints are active. I can toggle them, suppress them if necessary, and now I'll start the analysis again by starting here the session. Here I can change the aggressivity of taking away the material. Here in that area I can switch between stresses, displacements, or this is von Mises stress here. That are the main stresses. Okay, I can switch between them. Down there I can see the influence of my load cases. So that means the impact factors. I can sort them, and I can see, okay, load case 4 and 3, they have the most influence on my topology. And right now we see how ProTOp is taking out the material. During optimization process, I can change my targets here. As a target, I can take maybe boundary stresses or maximum displacements. All that kind of stuff is selectable. I could even, let's say, deal with eigenvalues to keep down my eigenvalues or to bring them up, to optimize the eigenvalues. And here we can see, okay, how this bionic structure is created with this technological constraint, 2 symmetry planes, and 1 B unidirectional open constraint. So that's one capability within ProTOp. And now I will bring in some, let's say, additional features like shells and lattice configuration. Therefore, I'm aborting again. Oh, it was already optimized. Target was reached. I will bring in here a new configuration. Therefore, I will, let's say, toggle one technological constraint. I'm toggling or suppressing this unidirectional open constraint, and now I want to deal with those surfaces here. I'm creating a new surface, maybe I call it loop. This belongs to this volume region here, and I can exclude here some surfaces. You see, okay, this surface will not be taken for later shell definition, so I just want to create around the highlighted areas some shells. So I will take this loop surface region for creation for new part configuration, and in that case it should be a shell configuration. I'm selecting my configuration data and I'm taking this loop area and I'm defining my shell thickness between 0 and 4 millimeters, and that's the ratio for the rounds and the chamfers. Okay, I can show that one here, and we see when I'm looking from front, this is about 2 millimeter thickness. If I'm going here for the upper limits, then I can see 4 millimeters, and if I'm going close to -1, it's not that close, then I'm getting a very thin area there, or shell. And ProTOp is allowed to go to -1. That means because I defined the minimum thickness as 0, it can take away a shell if not needed. Okay, so that's the first configuration I'm doing here with the shell, and then I'm going for a second configuration here. I'm adding a new, and in that case I want to do a lattice configuration. This should be done within, let's say, this volume region here I created before on the fly, and if I'm applying that one, you see, okay, these bars will be created. So I selected this bar here, and now I will do here another configuration with a honeycomb lattice structure. It looks like that by default, and I say, okay, it should not go to all of the material, I just want to feed, let's say, that material here. So only, let's say here, the right section will be created, and I want to move it here more a little bit to that direction. Therefore, I'm needing a new coordinate system, and I will, let's say, do a little bit smaller lattices here. And the lattices can change the diameter between 0 and 4 millimeters when I'm showing that one. Right now it looks like that. And now I want to use a new coordinate system, so I'm going here for adding new coordinate system, and the default coordinate system has to be turned by, let's take 6 degrees around X direction, was the wrong way, so I'm turning it back to that direction. And now with that coordinate system, you see, okay, it will be moved a little bit, not yet, because I didn't select a new coordinate system. Now you can see it very clearly here. Okay, that's the first configuration for my lattice structure, and by copying the lattice structure here, I will create a similar one on the, let's say, on the background, on that volume here, and therefore I'm needing a new coordinate system, and this has to be rotated in that direction by 6 degrees, and for sure I should use it here, and now we can show it. Okay, so quite easy to create my lattice structure, one to that side, one to that direction, and now I can check the behavior of both of them with the help of this design analysis. Now here I can see, let's say, minimum or actual configuration. That's actual configuration. We see here the volume, and of course here we see the lower limits, and we see the upper limits. And let's go back to the actual configuration. With that actual configuration, we are going for our optimization session, and we're starting the optimization session. Right now, our target is maybe to reach 34% of the volume. Let's switch here to the stresses, and we can see this area here. There is the low stress area. So ProTOp will take out this area with low stresses, and it will, let's say, increase only that area with the high stresses. So it's taking out now material in that area here. Okay, and the other bars, they're getting thick, thick, and thick. And now ProTOp is taking out the materials in that area. Now we are around 34%, and we recognize that our mesh here is quite coarse, and we think we need, let's say, some denser mesh to have better results. That's quite easy to achieve. We do not have to go back for our CAD system or FEM system. We just can go here for FEA model, where we have the capability to do some mesh refinement. I'm just going for doing mesh refinement on the, let's say, free design room, and here I'm just bringing in some more elements. I'm increasing here the number of elements, and now I'm refining the mesh. And you'll see the mesh is getting, okay, let's do it a little bit more. It's getting redefined, and I'm getting here quite dense mesh. Here I have some solver estimations. Okay, and now I can go back for my solving process. I do not have to start my solving process from beginning. I can pre-select here, let's say, a pre-optimized structure, and here in that session is my pre-optimized structure, and I will start with that one. So that means with, let's say, low RAM machine, I can solve quite a lot of elements here, quite a lot of big models. Here we see that our mesh is much more dense, therefore I'm getting much better stress results, and the optimization target should be maybe around 31%. So ProTOp is now taking out also that stupid elements there, and it's doing really, with a very dense mesh, a nice stress calculation. So I'm changing here the values for my stresses, and I let ProTOp optimize my component. Here in that area of my project here, I'm getting some information about how many elements, how many material types, load cases. All that stuff can be seen quite easily on this left-hand side. Here information about my configured parts and all that kind of stuff. Okay, optimization is quite close to finish. If I'm want to speed up the process a little bit, I can stop here the cycles. That's done right now. It's pausing. And now the, let's say, the topology on the screen is ready for further processes. I want to, let's go for smoothing and using this new Bionic structure for 3D printing or for validation calculation. Let's go here for the result tab, and in the result tab I can open even another session. Here I can see, okay, what was the old result here? Oh, I started with that one. I started here, or I ended here with that topology, and then I did some, let's say, mesh refinements, and now I have that topology. And this topology should be exported for 3D printing. So I'm taking all of my surfaces, and I want to do, let's say, some surface smoothing and some simplifying of that one. So I'm removing here some peaks. I'm redefining triangles. I'm smoothing surfaces. That takes a while. And I will simplify the surfaces a little bit. Okay. And these surfaces now will be exported for later use in my CAESS system or in my 3D printing system. I will do an export as a STL file in here my data folder. Okay. And I call it maybe for STL. Okay. And for my validation calculation later on in Creo Simulate, I will create some other surfaces. So I will just take my optimized area, that guy here, and I will do some surface smoothing, exporting only on that surfaces. I'm removing the peaks again. I'm refining some triangles, and I will smooth the surfaces a little bit. Okay. And I will simplify the surfaces. Okay. And then I will export the surfaces of my optimized region, but I'm going to simplify it dramatically, maybe in that direction. This simplification is done to be able to export, let's say, a meaningful OBJ file, and the OBJ file will be exported here. Okay. And I will use that OBJ file later on for doing my validation calculation. Therefore, I have to go back for Creo Parametric. In Creo Parametric, let's first just open the STL file. I'm setting the filter to all files, and I will use this STL file here, YYY. And this nicely smoothed model, of course, is triangulated surfaces, can be used for, let's say, direct 3D printing. Okay. As a next thing, I will use my OBJ file for recreation of my part. Therefore, I took my original part, or I'm taking it live, and I just cut it away here, this area. I'm going to resume that one. Okay, I'm just cut it away that area here. Okay, and this area should be filled right now with the optimized topology. So I'm going here for my freestyle feature in Creo 4. I will find here a new solution. This freestyle feature is free, it's not an additional module, and I can easily import here my OBJ file. So I'm taking here the OBJ file, this wavefront file, and I will use this geometry for, let's say, reconstructing my part. Going here before front view, and in the front view here I will create here on that area. I'm selecting, let's say, these surfaces here, and I will tell them you're right now sharp. Okay, I'm going back for my front view in order to select those, let's say, surfaces here. Okay, let's take them and make them sharp. Okay, that means later when they're sharp, I can, let's say, they can be connected easy with the original geometry. So I'm taking that area here. Okay, I'm doing it sharp. Okay, that's done. Let's go for another view here. Oops. Let's take the view AAA. In this view AAA, let's say here this line is horizontal. So I'm selecting those guys here. I'm making them sharp. And as a last area, I'm switching to that view here. And I'm selecting those surfaces. Okay, and I'm making them sharp. Okay, I'm finishing this process. These freestyle surfaces will be created. This takes a while because this is quite a complex structure. Okay, this is done right now. This is live demonstration, and I'm going here for my, for my surfaces, and I'm creating a solidify. So that connects now my freestyle area to, let's say, the fixed area. And with that construction here, I can go for my simulation application, and I can do the validation analysis. So going directly for Creo Simulate. Of course, in Simulate I copied that model here, and all the, let's say, loads and constraints are already there, and the only thing I have to do, I just have to set up here a new analysis. This analysis was created, we can display the study status. I created it about 1 hour ago. So here you can see I completed it 10 past 1, and it took me about 5 minutes to solve this solution. And when I'm going for my result environment, okay, post-processor is opened, and I can see here the results of this validation calculation. I want to see here the results, sorry. Now we can see the behavior of my component in Creo Simulate or in my original FEM system, and let's say that's closing now the loop of this demonstration. So I'm going here back for my Creo parametric environment. Okay, and let's go back for my slides here. So we saw right now the loop starting in Creo parametric. Yes, I didn't show live how to set up these forces, but that takes me maybe 10 minutes to set up forces and the volume region and defining some materials. Then we went for ProTOp, where we tested our model by doing optimization standard with volumes, and then we set up some shells and lattice features. We optimized, let's say, this structure here. Then we smoothed and exported the structure as an OBJ file. We got back to Creo parametric. In Creo parametric, or my CAD system, I was taking this OBJ file for creation of my Bionic part, and then I did, let's say, a simulation, an easy simulation in CryoSimulate. Of course, we can do that with even more complex structure. It's taking a little bit more time, but it's, let's say, the same process. And I think when I'm looking at my watch, I think we'll not have time to do that again here, this simulation, or just in a very, very short way. So I can go here very, very quick for, let's showing that very quick. Of course, you can set up that also in an assembly. So this is an assembly. The gray parts are fixed. The blue part is the design room. When I'm going here for my simulate application, I can see here also my forces and my mesh controls and my analysis. I can push here the run button. Of course, I should close the old application of ProTOp because of license regions. And then we can see, okay, when I'm taking that topology over to ProTOp, I have to import it here, then very, very easily you just can go in and say, okay, let's optimize this part. And then you say, okay, start the session. Of course, here the mesh is at the moment quite coarse, but we can behave as before, pre-optimize my component with coarse mesh. So we see right here it's taking out the material, and if you're coming out down to a certain level, then we'll bring in some denser mesh and do the optimization to our, let's say, desired limits. So we see right now, okay, it's getting quite interesting, my topology in that area, but we can see here, okay, these elements here, or the number of elements in that bar, they're getting quite small. Well, it's not that small right now, it's still okay. But as soon as we come down maybe to a volume around 30%, there seems to be a need, let's say, to do some mesh refinement. And I will do right now my mesh refinement. So I'm going here for pausing my application. Okay, I'm going here for my FEA model, where I'm just taking the optimization room, and I will bring down here, or I will increase the number of elements to a certain level. Okay, it's done right now, and I can go back for my optimization, and I can start the session again from this pre-optimized topology. So the first step will take right now maybe 20 seconds, and now we have much denser mesh, and now with that mesh we really can go close to the limits, maybe down to 15%, and see a very, very interesting organic structure of that component. So we see right now it's coming down. We're going for our stresses. We're changing the stress levels here, or we can see our displacements. Okay, our stresses, we can go for maybe a certain view. We're doing here again some cross sections. Come on. Now the cross section is here, and we can move our cross section in order to have a better overview of our topology. And of course, at the end of the day, I'm stopping right now the optimization process. Now it's about to stop. Right now, it stopped. Now it's still running. if you're in a hurry, you can, oh, now it's okay. Now we're taking, let's say, that topology, and the topology can be easily stored here in the result session, creating some surfaces. Okay, smoothing the surfaces. Okay, simplify it a little bit. Or I did not a lot of smoothing, I just simplified it a little bit, and here I'm going to export this as a STL file. Maybe here on the data, let's do UUUU. Okay, and let's go back for Creo parametric, and let's open the STL file UUU. Okay, and that closes the loop, so it's really incredibly fast with the help of ProTOp to create that kind of structures. That brings me to the end of the live session here. So last information, I mean, all these capabilities we saw right now in version 5.0 can be combined with non-linear studies like contact behavior, like plasticity. You can even work with pre-stressed screws, and we saw, let's say, the capability working with shells and lattices in order to optimize then. Because at the end of the day, when you deal with topology optimization, you really want to have a lightweight part. You want to optimize those components, and in the future, lattices will be there. You have to optimize the lattices, and ProTOp will do that for you. So that brings me to the Q&A sessions. Are there so far any questions? Because of the large number of participants, I would like to ask you to send me your questions in the question panel. Can you have shape controls for extrusion, meaning getting a structure that will be conducive to manufacturers? Yes, we can do that. I mean, with this, that was a question from Tulani. Yes, we can do that. No problem. With the technological constraints, we can bring in that information. And yes, I can show you that also later on in a separate web demonstration. Are there any further questions? I'm going right now for my chat panel. In my chat panel, I can't see right now. Any more questions? There's a question about recording. Yes, of course, you will get a link. You will get an email with a link on YouTube where you can download or see that demonstration. You'll get also a link on Dropbox to download the PDF of today's demonstration. So that will take, let's say, 1 day. Tomorrow you should get that information. Yeah, so another question, how many parallel cores can the software use efficiently? I would say my computer here includes 8 cores, as we can see it right now here, and they really can be efficiently be used. If you need further information, we can also get exact suggestions from CAESS as what they would recommend, but from my side here, at least 8 cores, and for serious, let's say, topology optimization, you should have 16 megabytes of RAM at least. Better is 32, and excellent would be 64 gig, not meg, gig of RAM, sorry. more questions. I'm checking my chat panel. I'm checking my question panel. Yes, doesn't seem to be more question about this topology optimization software. If you have any further questions, send an email. Here are the information. Call me. All the information should be on this documentation. So in the end, I just like to thank you for your time. I hope it was worth spending this hour having a look at the new exciting features of ProTOp. My personal opinion is this is really a very, very efficient tool. It's very, very fast, and it can easily connect to, let's say, all, or not all, to a lot of CAD system, to a lot of FEM system, and for the future with 3D printing and all that kind of stuff. This is really an amazing tool you should keep in your eyes. So thanks again for joining the webcast. Have a great afternoon and see you soon. Send me an email when you have any further questions. Bye-bye.